At this point, we've discussed a stem and leaf plot, which basically describes the shape of the data and a little bit of how it's grouped. Today we're going to discuss a box and whisker plot, sometimes also known as a 5-number plot. And this plot, you don't see all the numbers in the data set. You see some specific numbers. Before you, we have an example with those specific numbers identified. So you see the smallest number of the minimum, the highest number of the maximum. You see the median, those we know about at this point, and that's the number dead center in the middle. And now we have these two other numbers called a lower quartile and an upper quartile, which are basically medians between the median and the minimum and the median and the maximum number. And between that first and second quartile, we call that difference the interquartile range. All right, and to find that range, since it is a range, we take the quartile of the highest value, the third quartile, subtract the quartile value of the low quartile, and that gives us the interquartile range. So let's go ahead and do an example or two. So we've got an even number of data sets. Since we're finding medians, we know that it's between the two middle numbers. So again, let's just take and say there's 5 numbers here, 5 numbers here. The median lies dead center between them. So the average of those two numbers is 11, and that is our median. Now, we're not going to use that value in determining what our next quartile is. So you'll notice here there's a total of 5 numbers. And over here we also have 5 numbers. And the median between that high number and that low number is just the middle number, where we have 2 numbers on each side. So 6 is our first quartile, and in this case 2 numbers on this side, 2 numbers on this time. Our third quartile is 16. For an odd numbered data set, again, we know that we should have an equal number of numbers on each side of that median. So in this case, we know that we have from 18 to 12, that's 4 numbers, and from 8 to 2, that's 4 numbers. So that middle number of 10 is our median. Again, we're not going to use the median in determining our quartiles. So we have 4 numbers, 2 here, 2 here. Thus the average between 6 and 4 is our first quartile, which in this case is the average of 6 and 4 or 5. And then again, 2 numbers here, 2 numbers here. We're looking for the average of 14 and 16, which is 15. And that's Q3. Q1, we could find the interquartile range by subtracting Q3 from Q1 in each case. So as we've talked about before, there are some numbers that affect a data set in a way that's not necessarily representative of that data set. And those numbers are what we call outliers, or numbers that are pretty far removed from numbers in that data set. We see here's our normal 5-number plot or box and whisker plot. And here's this outlier sitting way the heck outside that. What determines an outlier? It's determined by if that number is at least 3 times away from the last data point in the data set. So the last data point would be what we would normally consider this max value here. Obviously, this outlier in this case would be that max number. However, since it's so far removed, we don't include it in that box and whisker. 1.5 times away, if there is a number 1.5 times away, we call that an outlier as well, but we mark it a little differently. Notice this outlier that's 3 times away from the data set is marked with an open circle, whereas an outlier that would be marked 1.5 times away from the interquartile range gets a little asterisk. So let's just say there was another one here. We'll just put a little asterisk right there, and there's another outlier. Okay. So now we're going to take and actually draw a box and whisker plot. The first thing we need to do is we need to arrange this data set in numerical order. So let's look for the smallest number. There's a 3. Next smallest number appears to be a 5. Next smallest number is a 7. Then we've got an 8. Looks like 12, 13, 14, 18, and then 21. So we count these up, and there's 4, 5, 6, 7, 8, 9 numbers. So we've calculated these values of the median before. We know that the median should be dead center between. I've got 4 numbers here, 4 numbers here. That means 12 is the median. I know I've got, in this case, 2 numbers over here, 2 numbers over here. I need the average of those two. So we take that, and our average is 16. That's my third quartile. We look over here, 2 numbers to the left, 2 numbers to the right. Average of that is 6, and that's the first quartile. And then we want to scale this so we have equal scaling or equal intervals between each number. So basically what I did was I listed all numbers from 0 to 24 to give me some space on both sides to work with, going by 2s, and then I plotted everything. So note I have my median here right at 12. I have my third quartile sitting at 16. I have my first quartile sitting at 6. The minimum value is 3, somewhere between 4 and 2, obviously, and 21 sitting between 20 and 22. So oftentimes we'll be asked to compare or contrast 2 different box and whisker plots, or even the meaning of a singular box and whisker plot in terms of how its data is laid out and what everything means relative to the data set. Because again, in that box and whisker plot, if you're only given the plot, you don't know all the different numbers. So let's give us an example. We've got the data in front of us that talks about a class is given one quiz and then another quiz. And we want to know, based on the fact that the first test came first, second test came second, was there a difference in the 2 classes? Was this the same test? Likely not, but maybe it was a pre-test and a post-test, or just a test after some teaching had happened. So if we look at this, there's a couple of things we can see right off the bat. One, the low number appears to be the same, the high number appears to be the same, and the median appears to be the same, and also the third quartile number appears to be the same. The only thing that really appears to be different is this first quartile value. Now this is kind of important because the low and the high, one kid scores the lowest, one kid scores the highest. It's going to be pretty common. But the fact that this number has moved up the first quartile in the second test and the first quartile in the first test are so different really is significant, because we know that each of these areas here represent 25% of the data. So we know 25% of the data is here and 25% of the data is here. So on both tests, we can say that 50% of the class scores below 12 out of 21, but on the second test, 75% of the class is above the score of 9 out of 21, which isn't great, but I mean, it's better than the other class where you say, well, 75% scored above 6 out of 21, which is pretty poor, So I would also say that definitely the second test, if this was some post-test and pre-test situation, the group as a whole did much better. further discussing, we can say, like we said before, the low, the high, the third quartile, all the same. The first quartile moved up from 6 to 9 from test to test. 75% of that class again scored above 6 on the first test, which isn't great, and 75 scored above 10, which is a pretty significant improvement. So I'd go ahead and say the second test was better or showed greater improvement than the first. So here's another set of data talking about testing, and one shows us a box and whisker of afternoon tests while the others show a box and whisker of morning tests. And again, we're going to be asked to talk a little bit about this and then draw some conclusions from it. And I think this is easier even than the second one, only because each of these data sets talk about 100% of the data. And you can see that in this case, 100% of the class is above roughly 72.5, while in this class, almost 50% of the class is below 75. So that's not great. So right off the bat, you're going to say, well, mornings are definitely better time to take tests than in afternoons, which kind of makes sense for many students, unless, you've got those early risers who are still half asleep. The other things we can state is 50% of the class is above a 7 or 87, whereas in this graph over here, we only have 25% of the class being above roughly 85. Likewise, 50% of the class is above 75 in this class in the afternoon, while above 87.5, 50% of the class is taking it in the morning. So to further summarize that, let's take a look at this. Again, we already talked about the 50% of the afternoon class, while 75% of the morning class was roughly, above that. Highest afternoon score was 93, and 25% of the class in the morning is roughly 93. That's pretty significant, considering this high represents typically one student. And definitely the two graphs show that the morning tests are typically better than the afternoon tests. So here's another set of data, and it talks about two lions, and basically those lions are being tracked, and as a result of tracking these lions, it talks about how far they travel during the night. And you can see that while this guy travels longer, he spends a majority of time closer, and while this one is shorter, it spends most of its time in a further range than this other one. Now, there are a couple of things, whether you know or not, about lions and their predatory habits. The males tend to stick around and guard the, I don't know what you call a herd of lions, but the group of lions, while the females are the ones who actually go out and do most of the hunting. So if you kind of know that, this graph makes a whole heck of a lot of sense. So we can make a whole lot of commentary on this, and let's just take a look at what some of that may be. They would have similar ranges if you were to take the high minus the low. This guy appears to be about 17 to roughly 03, and this one is about 15 to 2. So there's really only like one difference in their range. You see that Ramey, the one on top, the plot's wider than the other one, stating it travels further. Interquartile range for Mona is roughly 3. Interquartile range for Ramey is about 7-ish. All right, stating that Mona spends most of her time in between the 9 to 12 mile range, while this guy rarely ventures out of the 10-mile range and spends most of the time between a 4-mile and a 10-mile range. 50% of the Ramey's distances were concentrated between 2 and 5 miles. So again, staying close to home, charged with watching the pack or the herd, while the other person is tasked to go find food. So they may have to go further to find that food. And 50%, actually 75%, is spent between 9 miles and 15 miles. So as we can see here, we can make a lot of commentary based on percentages of data within these box and whisker plots. And that's probably going to be the hardest thing for many of you to do, is to just write sentences describing what you see in a graph and then making some conclusion based on top of that. All right. So again, the conclusion I make is this guy stays closer to home and this guy's further away. Whether you know that the female lion is in charge of the hunting and the male lion is in charge of the protection is kind of irrelevant. It just helps to talk about in terms of the data.